My name is Emanuele Di Lorenzo, and today I would like to discuss the use of empirical dynamical models, also known as EDMs, as a complementary approach to forecasting ecological indicators in marine ecosystem health. In this short talk, I will feature work from PhD theses of Tong Su and Giangiacomo Navarra as part of my involvement with the California Current Ecosystem LTER. I'm going to begin by putting forward my suggestions in response to two of the panel questions. What do you see as NOAA's role in enhancing and forecasting prediction? And what are the mismatches between what modelers are doing and what decision makers want or need? For this first question, I will try to make the case that NOAA may benefit from supporting grassroots efforts from climate scientists who are interested in applying their experience with the use of EDMs for seasonal and interannual forecasting to marine ecosystem forecast. And for the second question, I would like to suggest leveraging existing efforts in the community that aim at co-producing and agreeing on what are key ecological measures for ecosystem health that we may want to forecast. And these types of effort will help close the gaps between modelers and decision makers. So to get started, I want to provide a brief primer on what is an empirical dynamical model, why we refer to them as dynamical, and why they work. Now let us consider a relevant ecological indicator such as the Nyctiphenia simplex, courtesy of Mark Homan at Scripps. This zooplankton is a foundational species for the California Current marine ecosystem. Now suppose for a second that you were God and had the perfect equation describing the dynamics of this ecological species. And it looks something like this differential equations, where the rate of change of the zooplankton is equal to the forcing function f and a mortality rate defined by gamma. Now we can solve this dynamical equation on a computer by discretizing the dynamics as shown here. We can now rearrange the various terms to write a prediction equation for zooplankton, where the zooplankton at a future time is a function of zooplankton at a previous time plus some additional forcing term. In this simple equation, we have two coefficients of the discretized dynamics, alpha 1 and alpha 2, that are determined by the structure of the differential equation. We're now going to rewrite the equation as a function of the coefficients, and note that these coefficients can change based on the type of differential equations and also the accuracy of our numerical scheme. But in general, in any discretized prediction equation, we will have a similar structure where the zooplankton at a future time will be a linear combination of the zooplankton at previous times multiplied by the dynamical coefficient and the forcing terms. Now, assuming that we did not know what the exact dynamical equation of a system are, which is true for the most part of the marine population, in this case, if we had historical data, we can use pasteurization of the zooplankton, the forcing term, to estimate these dynamical coefficients statistically. Specifically, we can use the empirical lag covariances to estimate the coefficients of the dynamics, and for this reason, we refer to this approach as an empirical dynamical model. So let us try to use these empirical dynamics to forecast the zooplankton, and here I want to acknowledge work by Tong, who performed this calculation. So here we have the zooplankton data. For the forcing term, we're going to assume that it's captured by the climate variability of Pacific sea surface temperature anomaly, which we will reduce into principal components associated with the dominant Pacific scale EOFs shown here, which capture the large-scale dynamics such as El Nino, the NPGO, the PDO, and other regional scale variability that are contained in the higher order EOFs. So here again is the observed ecological indicator, and what we're going to do next is to perform a series of cross-validated prediction. What this means is that the data statistics used to derive the coefficients do not include the data that we're predicting. This is a key step so that we're making true predictions of a data space that the statistics has not observed. This allows us to understand how robust the statistics of the coefficients are, and in more technical terms, if they're stationary in time. What I'm going to show now are the cross-validated prediction for different leads. The one-year predictions are very skillful, with the correlation coefficient of R equals 0.8 between the observed and predicted time series of the zooplankton. This comes as no surprise because there's a great deal of autocorrelation in the data, which leads to inherent predictability at short leads. Here is the 2-year predictions with correlation skill of 0.68, and this is the 3-year prediction with correlation of 0.57. I want to point out that although we are focusing on the predictability of this EDM, this approach also allows us to further explore the relationship between the species and its climate forcing by analyzing the coefficient of the forcing and the associated patterns of the EOFs. So overall, this very simple EDM already shows promise for one-dimensional forecasts of ecological indicators. However, when we think of an ecosystem, additional predictability can also come from knowing and including in the model the state of several ecological indicators, right? We have essentially an ecosystem. So here is an example of a more advanced empirical dynamical models for climate and fish predictions that was developed using a simple linear inverse model, and this is work by Giangiacomo Navarra. Now, the shape of the differential equations here remains the same, except that now the state vector x here is a multivariate and includes a series of fish stocks, sea surface temperature, and sea surface height principal components. The dynamical equations, or in this case, the dynamical coefficients that we derived in the previous examples, are now captured by a lag multivariate covariance matrix G, which can be computed to forecast the state vector at different leads, for example, 1, 2-year predictions, and so forth. For this example, we will use the fish biomass data from the RAM database in a region that has already shown good physical predictability in the Western North Pacific, also labeled here as Area 61. Plotted here are the time series of biomass for different species along the y-axis from 1950 to present, which is shown in the x-axis. Each time series has its long-term mean removed and has been normalized by its standard deviation. So the color bar here is in units of standard deviation. Now let's use this EDM to perform forecasts for different leads between 1 month and 8 years, which are shown in this graph on the right. The y-axis is again the fish stock ID. The color bar is the correlation skill in reconstructing the time series for different leads in the predictions, which are shown on the x-axis. Here we can see that this EDM has significant skill up to 3.5-year predictions for most species, and in some cases even longer. We can now compare the skill of the EDM with the skill associated with persistence. That is the skill associated with guessing that the fish stock tomorrow is going to be what it is today. The persistence skill is shown on the left panel here and exhibits high skill up to 1 year. The persistence skill is a preliminary measure of the autocorrelation in the data. If we take the difference between the EDM and persistence skill, we find that the EDM can extend the skill significantly for up to 2 years. Now, this result, of course, is just for the purpose of illustration, but it does suggest that EDM may provide a promising complementary approach to forecasting ecological indicators in marine ecosystem health, and perhaps also help diagnose the relationship to climate forcing. So to conclude, I would encourage NOAA to engage in a grassroots effort to establish a working group on EDMs. There's a group of climate scientists that is developing a proposal for a Pisces working group on empirical dynamical modeling of marine ecosystems. The goal of this group is to bring together a multi-sector group to co-develop an EDM analysis and forecasting toolbox for human-relevant ecological indicators and marine ecosystem health. If you have suggestions of relevant people that will be interested in joining this group or could provide useful advice on how to shape the terms of reference and goals for this group, please do not hesitate to let me know. For now, the climate scientist group includes Matt Newman and Antonietta Capotondi from CU Boulder and NOAA, Stam Stevenson from UCSB, Tong Su and I from Georgia Tech. And collectively, this group has worked together and has a strong experience in the use of EDMs for climate predictions and diagnostic. The second suggestion is leveraging existing efforts to co-produce and agree on what are key ecological measures for ecosystem health that we may want to forecast. And this exercise will help close the gap between modelers and decision makers. And here I want to bring to your attention a recent project funded by the National Science Foundation entitled the Regional Ecosystem Services Observation Network, also called REASON, which aims to determine key biological aspects to observe to enhance coastal monitoring and provide a better understanding of ecological services and health. This project is led by Ali Burgess and Bob Miller. And I will leave you with this summary slide and thank you for your attention.